Good morning, everybody. Welcome to our weekly machine learning seminars. Today, we'll have the pleasure to have a presentation from Fateme Darlik from the Faculty of Science, Technology and Medicine, University of Luxembourg, who will present the topic that is already present on the screen about physics-informed constrained neural networks. Fateme, the virtual floor is yours. Please go ahead.
Okay, thank you for the introduction. So my name is Fateme. I am from the LuxStem group, and also I'm part of the D2 driven group. And today I want to present my work, which is using a physics-informed constrained neural network to predict the velocity of the particles. And I'm happy that this is my second time that I'm presenting in this machine learning seminar. So first, this is the outline of my presentation. To start with, I will have a brief introduction of what is my case and why did I choose that case and why I'm going to use the neural network there. And afterward, I will introduce my neural network and what is the physics-based neural network and why I add the constraint into my physics-based. And the next step is my results that I will present it and we can have a discussion over it. And at the end, I will present my conclusion. So biomass energy is a kind of a renewable energy that can deliver a significant reduction in a total carbon emission when it's compared to the fossil fuels. It can be generated or produced by burning the living or once living organisms, which we call them biomass sources. So usually the plant waste, the biomass sources can be divided to the three main category, like the wood, waste, and agricultural residues, that by burning them in the biomass power plant, we can heat the water, and the vapor from that water can spin a turbine, and by that we will power the generator and produce the electricity, and it's like the cycle of the biomass. The focus of my project is the burning part of the biomass sources, which is usually done in a combustion chamber. So in each combustion chamber, the biomass sources are entering the domain from here, from the left side. And after exposing to the hot air, they will be burned and produce the energy. And from the other side, the ashes are removed. Usually, the type of the combustion chamber that are used for the biomass cases, that they had the grate inside, and they can be constant or moving grates. And it's proven that if we have a moving grate, and when an already burned particle, because the moving grate can move forward and backward, then when the particles are on the grate, they can push back underneath other particles, and it will result to have an efficient and complete combustion. And here is the case that we simulated based on our combustion chamber. Now we just wanted to study the motions of the particles, and for the next steps, we will add the energy equations and the combustion as well. So here, as you can see, the particles are moving, and we define a periodic boundary conditions in the two sides. Then, because usually for the biomass sources, they had to enter the domain like in each time we have a mass flow. But what we consider here is that the amount of the biomass sources that are exiting from the one side, they will enter from the other side. We did these simulations by using XDEM, which is developed in my group, and it's in-house software that not only it has all the advantages of a discrete element method, but it has been extended as a thermodynamics state, strain and stress, and other things for each individual particles. you can visit our website for more information if you are interested. To solve this kind of problems, because this is the particles that are exposing to the hot air, we should use the coupling between CFD and DEM. So the CFD is responsible for the hot air. It will solve that in each steps, and the data will transfer to the DEM parts. That can be like the boundary condition of each particle, and we solve what happened to the particle, and then we transfer back. But the idea is here to replace the DEM part by our surrogate model, or by getting the help from the neural network, as because due to the high number of the particles that we have here, and because these simulations, the real time for the simulations like 1,000 or 2,000, so it's really time consuming, and that was the reason that we thought of replacing the DEM part by our neural networks. So the type of neural network that we use here is the physics-informed neural network, but like a simple neural network has some inputs, some hidden layers, and the outputs, and usually the loss function, which in my case is mean square error, is the difference between the predicted data and the exact data. But then we move to the physics-informed neural network. We add another term to our neural network, which is here is the equations, or the PDE equations. And in this case, the loss functions not only has the term for the difference between the predicted and exact data, but it also will check that if our predicted data will satisfy our PDE equations or not. So, for example, if you have a function, PDE functions like this, then your loss functions will have two separate terms, one for the just variables and another one is for the equations. And then these differentiations here is done by automatic differentiations, which this AD exploit the fact that every computer program, no matter how complicated they are, they will have a sense of like some elementary operations or functions like addition, subtraction, and like. But we also add another term there, which is the constraint, and this is due to the physics of our problem. So here, because we have some grade that the particles are moving there. So if the velocity cannot keep the particles on the grid, and it will force them to go like beyond the grid. So it doesn't. So the physics of the problem would not be satisfied. So we add another term to our loss function, which choose the velocity, and that the particles will stay above our grid. So it is the geometry constraint. On my first presentation that I had in this seminar, I talked about that to solve this DEM, to replace this DEM with our neural network, I did the projections between the particles and my CFD mesh. And I used the Navier-Stokes equations, and I checked that if this Navier-Stokes equation can predict the motions of the particles. But in this approach that today I'm going to talk, it's that I just apply my neural networks to the particles, so I don't use any CFD parts, and it's just purely the DEM part of the coupling. This is how my neural networks look like. So my input is the time and the coordinates. It's the 3D, so X, Y, Z. And I have some hidden layer here. And my output is the 3 velocities. And the equations that I used as my physics inform is the force equations in the 3 directions. So if I do that, then my mean square error is the summation of the all 3 velocities and these 3 equations that I added to my neural network. But before all else, training and testing a neural network needs to identify the structure of the neural network. To do that, I did a fine tuning of my hyperparameters. So in this case, I just choose a number of 20 for my layer, and I did the tuning for my neurons. And as you can see in the right plot, is that by increasing the number of neurons in each layers, the train loss function is decreasing, but it doesn't have it. The validation loss function doesn't follow the same procedure. So after some points, it will started to increase the value. So here is where we started to have overfitting. Then we choose the 8 number of neurons for our in each layers. And in this diagram, it shows that in each number of neurons, you have to repeat your neural network for several times, because in each time you might get a different loss functions. After choosing the architecture of our neural network, we go for the loss functions. And by monitoring the loss functions, we did the early stoppings to again avoid the overfitting. So, for example, after this point, you can see the validations loss function is increasing. So this is the things that we did before doing our training. But after do the training, I just so after the training, to illustrate the effectiveness of our current approach, I plotted these three diagrams, that each of them is for each velocity. In a x directions, this is the time, and in a y direction, we have the percent error. So this is the time average mean absolute percent error. It means that we calculate the absolute percent error for each particles in each time, and we did the time average based on that, and then we plotted this diagram. And as you can see, for each of them, the percent error is the maximum is 1.2%, and for the velocity in a y and z directions, there are even less than 0.5%, which shows a good agreement between the predicted and the exact data. But to make it more like visible, okay, here I show the particles velocities in some certain time steps, and which in the right side you can see the predicted velocity in the x directions, and in the left side is the exact velocity, which we have it from our XDM simulations. And here is the difference between these two, the predicted and the exact data that we have. But as you can see, the majority of the particle has an error between 0 and 0.4, I can say. And others are mainly in 0.5, and there are some rare particles that has a more velocities, more absolute error. And we can say that, for example, in this region that we have our grade, it can be because of the sudden changes that when the particles will move from one grade to other grades, they are falling down of the grades. and the velocity is has a sudden change on it. So the neural network is not able to capture that sudden changes. And it is the same, almost the same diagram for the velocity in y directions. And here the error is less than the velocity for the x directions. And here I think when we check like 5 or 6 particles has the velocity upper than 0.2, and all others has the sorry, I'm saying that I mean the error. So just some of the particles, some has the error more than 0.2, and all others has the error between 0 and 0.2, and all of them are in the percent. And we have the same one for the velocity in the directions, and the same thing is happening for all of these velocities, which shows a good agreement between the predicted and the exact data. But here is what I'm working on currently, and I wanted to continue, but I really wanted, if you have any idea regarding that, if I will be able to do that or not, just let me know, because it's like I didn't finish this part, but I like to present it to see your idea. So here it's a time diagram which we did our this XDM simulations between time 0 and 100, and we just got the time. We choose our training time between 20 to 100, and we deleted the first 20 seconds because we wanted to our case would be like more stable or steady. But now we wanted to see if our already trained neural network is able to predict the velocity of the particles for time more than our training time. So we did our training between 20 and 100. We wanted to check if we can use it for time more than 100 to 120. So what are we doing here is that we got the particles positions here, and we feed it to our neural network. Our neural network will predict the velocity. We use that velocity to calculate the new coordinates, and then we again feed that coordinates to our neural networks, and we go further and further. But the delta t that we can use here, it's not necessary to be the same delta t as our XDEM. So here I make a GIF for different delta t, which is our XDEM delta t is 0.001, but I started from that 0.01, 0.1, and 1. And after applying this approach to my particles, it shows that nothing strange happened to the particles, like they are like moving upward or such things. But we are still working on that to see if it's able to predict it correctly or not. And in terms of time, so if I wanted to give the delta t as the same of my XTN delta t, so my neural network would be more time consuming than my XDM. So as you can see, if I just did it for 10 seconds, and it's almost 3,500 seconds for the CPU time, as the 100 seconds for the XDM is like a double this. So if I wanted to make them to be comparable, it would my neural network would have like a would need 5 times more CPU time than the XDM. But the things about the neural network is that you don't have to just use the same delta t, so you can increase the delta t. So if here in this column and the XDM column, the simulations time are the same. And but the CPU time here is less than the CPU time for the XDM. But also it works until if you put the delta T1, and you can also get the same result, which if for the delta T1, we can do the simulation time like 100 times than the XDM, but we still get the CPU time half of the XDM CPU time. And yeah, this is the end of my presentation. So I did the tuning, fine tuning of my neural network hyperparameters, and I compare the error between the exact data and the predicted data. And also I use the physics informed constraint neural network to apply my geometry to my neural network. And yeah, at the end I try to predict the particles motion for time more than training time. And I compare the CPU time, which shows that the neural network will need less CPU time when it's compared to the DEM method. And thank you for listening. If you have any question or suggestion, I would be happy to hear.
Thank you, Fateme, for your presentation. Now let's move to the discussion part of the seminar.
Sure.
So whoever wants to talk, just switch on your mic or raise your hand. And I can see a question in the chat already from Michał Habera. The question is, why is the error in percent? Why the error is called absolute while it is in percent?
Okay, so I just didn't put the equations for the error, but
is it a relative error or absolute error?
it's the absolute error.
So error of what?
Okay, sorry. Maybe it's a relative error, but it's the difference between exact and the predicted data divided by the exact data.
Okay, so this is the relative error.
Okay, sorry.
Mm-hmm. I may have a question. Okay, I can see Vasilis has one, and
yes.
Okay, Vasilis, please go.
Okay, thank you. Thank you very much, Fateme, for your presentation. I'm kind of interested in physics-informed neural networks. I haven't used them on my own, but I find them interesting. I don't know in the future if they will play an important role, but it's always nice to see presentations on them and get used to them a little bit more. I do have like a few questions. Like if you go to the slides for the loss function, where you have that you said that you have three parts, three terms, if I remember correctly.
Okay.
Here.
This is the last function of my work.
Okay, so first of all, do you have some data, or is this a data-free methodology? Because I didn't get that, to be honest. Do you have any training data?
Yeah. So my training data is the data that I gather or collected from the XDEM simulations.
Okay.
So we have the XDEM, we have the DEM simulations, like the velocity or the position of the particle. I get the data, and I use the 70% for my training data and the other 30%.
Very good. Yeah. Okay, thank you. So one part of your loss function is how far away your network prediction is from the data. And again, the second one is the Navier-Stokes equations. How if you satisfy them or not?
Yeah, you know, here in the presentation that I had before here, it was the Navier-Stokes equations that I add to my physics info. Okay. But in this case, they are not Navier-Stokes equations, but doesn't make any difference. So how does it? How can I check that if they are satisfied or not? It's that there's the AD, the automatic differentiation, that is already applied in the TensorFlow, or if you are using cross-border neural network. So based on the the TF gradient that you use in your TensorFlow, it will do the derivatives of, for example, derivatives of the u and your coordinates. So usually is your output on your inputs, and then it checks that if your equations are reaching the zero or not. So yeah, both the difference between the exact variable and predicted variable plus your equations, all of them is your loss function. They had to go to zero.
Very good, thank you. And is there a third part? Because you mentioned that you have a third term in your loss function, didn't you?
Yeah, that one is for the geometry, for my geometry, because I have the grade, grade that the particles are moving. So I check that if the velocity that is predicted by my neural network wouldn't force the particles to go like beyond the grade. Because of the physics of my problem.
I see.
Because I wanted to use it to predict the velocity of the particles for time more than the training time. So maybe in my training time, I wouldn't face the problem if I didn't add that constraint.
I see.
But yeah, I need it for the next one.
So is this constrained? Do you apply it during inference as well somehow, or is it just during training that it is?
It's just during training.
Okay, I see. And so without it, did you try to see if you get this problem? And you do get it.
Yeah, I did it because my first method I just used physics inform, but now that I'm going to predict for time more than the training time, I add that one if it will keep the particles on the grid.
I see. Okay, good. And so basically my second question or comment was about that, about using your neural network beyond, outside of your training domain. And I don't know, for me, I'm not familiar with physics informed neural networks, but for classical ones, let's say, for non-physics informed, I wouldn't do it, because we know from theory that they extrapolate and the prediction is very bad. So why do you expect, why do you think that it is a good idea to make a prediction outside of your training time? Do you have an intuition behind that? How did you came up with that idea?
Yeah, because the case that I'm working on is a real biomass cases. And we were thinking of if we could do the extrapolating into the time, like the predicting for the time more than the training time, then it will reduce the calculation time a lot, and that would be helpful in the industrial applications when they don't have that time, and if it's applicable. But we are not that sure yet, but we are just working on what we can do, or what else we had to add to our neural network to know what is going to happen for the...
Is there literature either in the physics informed area or in the time dependent problems solved with machine learning indicating that you can actually use neural networks to predict in the time domain beyond your training time? Because I in my head, maybe the physics is quite different if time goes beyond your the range that you trained on. So is that decision supported by some other paper, or is this just something that you are exploring, which is fine? I'm just wondering, basically.
Yeah. No, I haven't seen some documents in a... I saw that some people are trying to extrapolate using the networks to be able to do the extrapolating, but for the time, no. I didn't see any.
Very good, interesting. I hope you're right. It's going to be very interesting, and thank you for your presentation and your answers to my questions again.
Thank you.
Saurabh? do you want to ask questions? I can see that you raised hand.
Yeah. Thanks to Vasilis, he covered some of my questions. And Fateme, thanks for the presentation. But I have one question about the same that you're using the network to predict beyond your training time. Do you have any error values or some solutions with respect to the true solution, how much the solutions are deviating from true solutions? Can you go to that slide?
I didn't present it here, but you mean that if I can predict these motions to what happened in the reality, like in simulations?
No, I just wanted to know, like you have the simulations here now. Do you have plots for error, percentage error, like you have for the previous ones? And how those errors are different than the ones where you use the network to predict on the data which was within the training set?
Yeah, here I have the exact data as well, but the aim here is not to get the same velocity at what is happening like in a reality. Now that we are focusing on that, if it will like, if you just saw the particles, they are like moving due to the physics and what should happen to the particles, like they are not against the gravity or they are not going like in the z direction or such thing. So because our aim is not to compare the results of these to the actual cases, we didn't do that because in some points we are completely sure that they are behaving completely differently, maybe to the actual velocity that might happen to the particles. But now we are just focusing on that if we can see that if the particles are behaving correctly, to just comparing to the physics of the problem, not to the exact data. So no, I didn't compare these predicted positions to the exact position.
I think that would be interesting if you could do that, because just seeing some simulations and visual things won't give any insights in knowing how correct the solutions are, or
Yeah.
Okay, thanks a lot.
Okay. Thank you for question.
Onkar?
Yeah, can you hear me?
Yes.
Yeah. So the thing about when you talked about you want to predict after training time, right? Some sort of extrapolation. I guess my only concern is it might work, but the thing is, for example, if you have a stiff solution, if you have a stiff equation, then you don't know whether your solution will blow off or not, right? So that is the concern. And other than that, this is at the end, it's a data-driven method. It's not it's not that we are solving that particular equation. We are just assisting it, right, for our neural network. So you could try it. It's a really interesting, I guess, idea. But I'm just concerned if your equation is stiff, it will not work. But if your equation is not stiff or it's already well stable, well balanced, then it will work, I think. So that was the thing. And my question is actually, so how many hidden layers you have used for this your neural network?
You mean the number of neuronal layer?
Yeah.
Yeah, so I have 20 layers and I have 80 neurons per each layer.
Okay.
Yeah, that's quite a large.
And how are you implementing this constraint which you talked about, this geometrical constraint? I was interested in it actually.
Yeah, for me, because the main concern of my constraint is the velocity in the y direction, because I don't want the particles like to go beyond the gray. So each time it's calculate the velocity in a y directions, it calculate the y coordinates to see if they are still like upper the grades or not. And if it's not the case, we will project it to their actual position. So we will change the predicted velocity based on that.
Okay.
It's kind of, I think, new things, this constraint neural network. I saw some papers on it from, I think, the people from the Belgium. But yeah, the idea is quite interesting.
Yeah, that's
Because
why I asked, because you're putting a geometrical constraint, not some physical constraint. Yeah.
yeah, you can apply it for like a material properties or such things if you have any constraint in your mind. Because, for example, they shouldn't be like negative or such thing. But for me here is just the geometry constraint.
Yeah. Okay. Thank you very much.
And thank you for your suggestion and your question.
May I have a question to you, Fateme?
Sure.
I'm not sure if I understood fully the framework that you are using. What I mean is that I'm not sure what is the input to your neural network. Is it the position and time of a single particle, or this is the vector of the whole system that you are feeding in as the input to your neural network? So question whether you are analyzing the behavior of a single particle by particle by your neural network, or you're analyzing the whole system at once. So this is in the training in particular.
I can go back to the okay, sorry.
And the question that is linked to this is how do you deal with this inflow and outflow of particles through the input of your grid and output of your grid, because the number of particles changes in time.
Yeah. So for your first question is that after I did the simulation, for example, for the DEM or XDEM, I got all the data like time and coordinates and the velocities, and I mix the data and I choose randomly like 70% of the data to as my training. So this is
but what's the data? I mean, is it the particle by particle that you are feeding in, or you are feeding in the whole vector of positions for all particles at a given time?
No, it's just particle by particle and time by time.
I see.
Recurrent. It's not the recurrent neural network. It's just so each. So for example, if I have a 2000 particle in a 10 time, so each of these x, t, and y, they have a 20,000 data inside, and it is the same for the velocity. So
okay, so you have a neural network represent the behavior of a single particle.
Exactly.
That somehow takes into account the behavior and the history of the whole system that you're analyzing, but you don't have any control parameters that are able to memorize this change of your state of the system. Yeah. And the question is the second question: when you are producing your input data, do you have any run-in period for your XDEM simulation? Because let's look at the time. If you start from some setup of your system,
yeah,
the time is 0 for every particle, wherever they are, right? Yes. And only after you just move the one cycle of the whole particles, you have the time that is, let's say, more relevant maybe to the steady state process. Yeah. So do you do anything like this, like run-in?
Yes. Here, I showed that we deleted the first 20 seconds.
Okay.
We started from the time 20 to be sure that they are more like we have a more steady state things, or they are more stable and everything is under locations, and then we just get the data from the 20 seconds to 100. So that's exactly that happens when the particles are in their initial conditions, and then when they wanted to just suddenly start. That's true, that happens, but we just started from the time 20 to avoid these sudden changes.
I see. So you don't have any state variable that would model the time dependency of your system?
No.
Okay, so it is like a dynamics of a single particle that maybe depends on time, depends on the position, but does not depend on the history, does not depend on the surrounding system. Am I right? I mean, your neural network prediction.
Yeah.
Because you don't have any input to somehow provide this additional information to your system.
Yeah. Yes, exactly.
And then after having this particle by particle prediction of your neural network, you will receive as an output, you receive the velocities. You can compute the first derivative of the velocities because it is trained. I mean, it's physics informed part. So you have the accelerations, and then you apply some dynamics, like some time integration scheme, like you usually do in a discrete element method. Am I right?
Mm-hmm.
Some forward Newton or some leapfrog or whatever else.
No, I just used this for when I wanted to predict for time more than training time. But during my training time, no, I don't do that.
Yeah, but I mean, after you want to predict the flow of your system by this neural network surrogate model, how do you use it in practice? Because the prediction is the velocity and the acceleration possibly. And but this is given for a given state of the system. And I guess your idea is to be able to predict the whole process with your neural network. Am I right? Or just a single increment of your system?
Just let me say it in another way. When I use the physics-informed neural network for my training time to reconstruct my velocity field. So what I'm doing here, I didn't use all my velocities that I have to do the training. So I just use part of them to do the training of my neural network. And based on that, I reconstruct all the velocities in all the time steps during my training time. So if for example, if I get it like at that time, the particle that is on that position, what is the velocity of that one? So that neural network will predict it for me. So
I see.
The reconstruction, the field of the velocity.
Mm-hmm.
And
Okay,
then,
I see.
yeah.
But do you have any, let's say, how would you then apply your neural network in some real life example? Let's say that you want to use it to solve some problem that you usually solve by extended DEM, because you have some interaction between particles, and the velocity changes because of the whole configuration of the system that changes in time and is very unstable. So how can you, let's say, do this with your neural network while it provides some sort of error? And I'm not sure how it is able to take into account these interactions, because you only analyze a single motions of a single particle without any knowledge about surroundings. So can you comment on that? How would you deal with this?
Yeah. There is two different things in my works that I've so far worked on. So first one is the one that you are saying, is that the one that I did so here, because I see that the CFD and DEM should be we have the coupling between CFD and DEM. What I did here is that I just get each CFD cell, and I did the projection of the particles in each cell. And then I solved the Navier-Stokes equations, like the Floyd equation, the CFD equations for each cell. So in each cell, I had the velocity and densities, which is the average velocity of the particles and average mass of the particles. And to calculate the pressure, I use the force interactions between the particles to do the pressures. But in my current approach, what I'm basically focused on is just to predicting the velocities, and then to use that for the time more than the training time. So
I see the point.
The first time that this not the first time, but the people the person that who suggested this physics-informed neural network, like Maziar Raisi, he was using it when in experimental cases you just have some velocities, like some discrete data like velocities, and based on that you wanted to reconstruct your whole field. What you can do is to use this physics informed neural network. So my first part of this neural network is just it got some velocities and make the whole field based on that velocities. But here I use it for the discrete for the particles motions. So if I have some velocity of some particles in some time, then I can see what is the velocity of others based on the things that my neural network has been trained.
All right.
I don't know if I give the answer to your questions or no, but
yeah, I mean, I have some idea, but of course, I will ask you in person later on.
We can discuss it later.
Mm-hmm. Sure. Thank you.
Yeah.
I had also some maybe one comment or question to one of your first slides. In which you show some general idea that you are looking at the second derivatives as well. Here, yeah.
Sorry.
Okay. All right, and you were looking for the second gradient of your positions, like the square over the x squared.
Yeah.
And I think for some activation functions, it is 0 always, because if you use for instance relu as your activation function, then for a given input it is linear or 0, and then the second derivative with respect to x, with respect to your input, I guess it will be 0 normally.
Yeah. Yeah, the activation function that I'm usually using here is the sine or tangent hyperbolic based on the normalization that I'm doing on my data. But I'm not sure if these automatic derivatives is
for nonlinear ones, probably it won't vanish. It won't vanish, of course.
Because it is the gradient for the output and the input, not the output and the layer before. I'm not sure if you use like a ReLU activation functions, which will apply like this layer to this layer, would affect the second gradient here, because this is the gradient of your output and your input.
Yeah.
I didn't try that because it's not the case for mine. But yeah, this is.
I think that if it was ReLU, it would be 0 by definition.
Okay.
But also I can be wrong, of course.
Yeah, I don't know too. Yeah, because we are usually use the sine or tangent hyperbolic.
Yeah. If it is nonlinear, probably it will be.
Yeah.
For sure, it won't be 0.
Yeah.
Okay, I cannot see any more question. So, oh yes, there is Vasilis who is raising hand. Maybe
if we have time, I would like to make one more question. Basically, I'm not 100% sure. So for your training data, is it one simulation only?
Yes.
Okay. So you have a specific geometry and a specific a set of input conditions, input velocities, let's say. And like, do you hope in the future to maybe train on 5, 10, 100 different scenarios and try to make a prediction like for a different geometry, like from the one in your training set? Or is this not something that you're interested in?
Currently is not the case for what I'm working on, because it is like a biomass combustions and it will always have this same geometry I'm using. But I can think about changing like the initial conditions and the boundary conditions, such things. But now, no, I'm not working on that, because it's just one case and I'm just seeing what ability it has based on just one simulation.
Okay, very good. And okay, that's it then. Thank you very much.
I think that was a good question. Thank you.
Yeah.
All right, thank you, Fatim, for your presentation and the discussion, and thank you to all of you for the discussion. So we'll be finishing, and let me invite you for the next week. We should have a meeting next week, and I will share with you the details later on. Have a good day. Have a great weekend.
Thank you for the invitation.
Later on, and see you soon. Bye bye.
Goodbye.
Bye.
Thank you, Fatim.
Bye.